We're going to do a bit more on slopes now. You've seen this sort of thing before, a simple graph, x, there's y, and we have some sort of a line that describes this relationship between x and y, and you have 2 points on it. You might have y equals 10 when x equals 8. We'll call this y1, and this is x1. And the index terms, the ones, indicate that they're a matched set, 1 with 1. Then we might have another possibility. This might be 8, and that would be y2. And y2 is associated with, say, 9, which is x2. So we have this matched set of x1, y1, x2, and y2. And what we want to be able to find is what is the change in y over the change in x. Well, the way we'd write that is, and you got to be very careful, that would be y1 minus y2 over x1 minus x2, which in this case is 10 minus 8 over 8 minus 9, which equals 2 over minus 1, or it's equal to negative 2. So you have a negative slope. This slope sign is extremely important. What this is telling us is if x goes up, then y goes down, and if x goes down, then y goes up. That's all very, very convenient. Unfortunately, in a heck of a lot of cases, the world is not really linear like that. And that means that the slope is not constant. That is, the trade-offs between x and y aren't at a fixed proportion, but they move. That proportion changes. So we go from a situation, the linear world, where y equals some intercept term plus some slope term times x, to a more generalized version where y is just some function, we'll define it later, of x. So it depends on x in some way, maybe linear, maybe nonlinear. Well, one of the great wonders of Sir Isaac Newton, and actually of Leibniz as well, who came up with different notation for the same idea, is how to measure the slopes in a very, very interesting fashion and for a nonlinear world. So let's suppose we have something that looks like this. We have y, which is our dependent variable, depends on several things. One, a, which is a constant. It's going to be some sort of number that doesn't move. So a is a constant. It also depends on x. This might be our control variable, but it's an independent variable that moves, and that generates some movement in y in a systematic fashion, and n, which is an exponent. Also a number. A couple of notes on exponents. One, and this should be a review for all of you, anything taken to the 0th power equals 1. Another thing to keep in mind is that 1 times x just equals x, which is a nice disappearing, vanishing act on the part of 1. It comes and goes with relative ease. Another thing to keep in mind is that x to the 1st power is just equal to x. We don't write the exponent when it's just equal to 1. And lastly, x to the minus 1 is equal to 1 over x. That the negative exponent puts the value of x in the denominator. So those are the basics that we're going to be dealing with, and what we're trying to find out is what is change in y over change in x, but a simple subtraction problem won't work because this is going to be moving. We want to get the instantaneous version of that, or a small change version of that, which is this dy dx. That's what we'll be working on for a while, and hopefully after a while it will become clear why we might want to do that. Let's suppose we have a relationship that looks something like this. We have x on this axis, we have y on this axis, and we have a relationship that goes like that. This is y equals some function of x. Oh, I ran out of space there. Have to write it somewhere else. This is y equals some function of x. So that's what we have, and we're very interested in understanding how y changes with x. So that finds the slope. So if we have something that is y equals a times x to the nth power, then the slope of that, dy dx, is fairly straightforward. You take the exponent down, that's n, keep the a where it is, the x where it is, and subtract 1 from the exponent. That's all there is to it. A couple of quick examples here. Let's suppose the actual nature of it is that y equals 10x cubed. Well, in this case, a is equal to 10, n is equal to 3. So dy dx is equal to, you take the 3 down, the 10 stays where it is, the x stays where it is, 3 minus 1, so we get 30x squared. This becomes valuable. Hopefully you'll recognize this. If this is x1, and this is y1, and you think about the slope at that point, the slope looks something like this. If we're going to draw a straight slope, it looks like that. It's positive, not very steep. If we were then to look at, say, x2, which is out here, and y2, and we looked at the slope here, it's much steeper. That slope is changing. Well, you notice that this slope changes with the value of x. So this slope is capturing those movements in y and x and allowing us to gauge how much they actually move at any given time.